Okay, so in this session, we are going to look at conditional probability mass functions involving two random variables. We didn't actually have a chance to do this in the summer session this time, but for the sake of completeness, I thought I'd so remember we had conditional probability. So the probability of an event A given an event B is the probability of A intersection B divided by the probability. Okay, and that gives, if you multiply both sides by the probability of B, that gives you the multiplication rule, that the probability of A intersection B is the probability of A given B times the probability of B, provided that the probability of B is not equal to 0. Now, we want something similar for two discrete random variables. I would like to know what the probability of X is. The probability that X is equal to X given that Y takes a value of Y. So that will lead us to the notion of a conditional probability mass function. Okay, so if I had a probability mass function, what would it look like? Is there some analogy to the analog, sorry, to the multiplication rule, an analog to Bayes' rule, and to the theorem of total probability? Okay, so this is an example that we're going to use to illustrate some of the concepts. So you roll a fair die, that's the experiment. The sample space is rolling a 1, 2, 3, 4, 5, 6. The random variable X takes the value of the roll, Y takes the value of 1 if the roll gives an even number, and it takes the value of -1 if the roll gives an odd number. As an exercise, let's construct the joint PMF for X and Y. Okay, so you should recall that the joint PMF evaluated in X and at Y is the probability that X is equal to small x, and at the same time that Y is equal to small y. Okay, so let's work this out for a few terms. The joint PMF evaluated at 1, 1 is the probability that X equals 1 and that Y is equal to 1. Okay, that's the probability that X is equal to 1 and Y equals 1. In terms of the sample space, that's the probability that you rolled a 1 in intersection with the event of rolling a 2, a 4, or a 6. The intersection of these two subsets of the sample space is empty, and the probability of the empty set is 0. Okay, so given that, you should be able to show, using the same reasoning, essentially, that the PMF evaluated at 3, 1, and then the PMF, the joint PMF evaluated at X equals 5 and Y equals 1. These are both also 0. Now let's work out the joint PMF at 2 as X equals 2 and Y equals 1. That's the probability that X equals 2 and that at the same time Y equals 1. Well, the probability that X equals 2 corresponds to rolling a 2 in the sample space and is intersection. And Y equals 1, Y equals 1 means an even roll, and the even roll means rolling a 2, a 4, or a 6. If we look at the intersection of those two sets, that's getting a 2, and the probability of getting a 2 is 1/6 for a fair die. Okay, with the similar reasoning, you should be able to show that the PMF for X equals 1 and Y equals 1, and the PMF for X is equal to 6 and Y is equal to 1. They're both 1/6. Okay, we've done enough cases using the same reasoning. We should be able to show that the joint PMF for X equals 1 and Y equals -1, or X equals 3 and Y equals -1, or X equals 5 and Y equals -1. All those joint PMF values are 1/6. And the joint PMF values for X equals 2, Y equals -1, or X equals 4 and Y equals -1 or x equals 6 and y equals -1, those joint PMF values are 0. Okay, so we found in all the f sub xy for all cases, and we're going to use this a little bit later. So now we define the joint PMF, the conditional PMF from the joint and the marginals. If x and y are discrete random variables with marginal PMFs f sub x and f sub y, and you have a joint PMF f sub xy, then the conditional PMF for x given a value y is, we use this notation, x given y. That's equal to the probability that x equals x and x equals y divided by the probability that y is equal to y. All right, whenever the probability that y equals y is not 0. Okay, now if we multiply both sides by the marginal, we would get that the joint PMF is equal to the marginal PMF is equal to the conditional PMF times the marginal PMF. Okay, returning to the example, the marginal PMF, the probability that x equals 1 given that y is equal to 1 is the joint PMF that probability that x equals 1 and that y is equal to 1 divided by the probability that y is equal to 1, which is 0 over probability of getting an even is 1/2, and that's equal to 0. Okay, the probability that x is equal to 3 given y equals 1 is also 0, and the probability that x is equal to 5 given that y is equal to 1 is also 0. That is an exercise. Let's say another value. The probability that x is equal to 2 given that y is equal to 1 is the joint PMF, the probability that x is equal to 2 and at the same time that y is equal to 1 divided by the probability that y is equal to 1. Well, we found the joint PMF evaluated at 2, 1 was 1/6, and the probability of y equals 1 means the probability that you've got an even roll, that's 1/2. So 1/6 divided by 1/2 is 2/6. Similarly, you should be able to show that the probability, right, the conditional PMF evaluated at x equals 4 and y is equal to 1. That's the probability that x is equal to 4 and y given that y equals 1. Similarly, the probability that x is equal to 6 given that y is equal to 1. These two conditional probabilities are also 2/6. Then we do some cases with y is equal to -1. The conditional PMF at x equals 1 and y equals -1. That's the probability that x is equal to 1 given y is equal to -1. That's the probability that x is equal to 1 and y equals -1 divided by the probability that y is equal to 1. Well, we found that the joint PMF is 1/6 in this case, and the probability of rolling -1, okay, that should be a -1, is 1/2, and so that's 2/6. Similarly, we should get that the joint PMF for x equals 3 and y equals -1. That's the probability that x is equal to 3 and y equals -1. And the probability that x is equal to 5, and given that y is equal to -1, these probabilities are also 2/6. Okay. The probability that x is equal to 2, given that y is equal to -1, that's the joint PMF evaluated at 2 - 1, which we found was 0, divided by the probability that here y should be equal to -1, not 1. That's a typo. And that's equal to 0 over 1/2, which is 0. Similarly, you should be able to find that the conditional PMF, which is the probability that x is equal to 4 given that y equals -1, and the probability that x is equal to 6, given that y equals -1. Those conditional probabilities are both also equal to 0. Okay. Now f sub xy, xy, so this should be 2, 6, not 1, 6. Sorry. So these are 2, 6 for x equals 1, 2, 3, and y equals -1, and 2, 6 for x equals 2, 4, 6, and y equals +1. Okay. Some properties of the conditional PMF. PMF goes from, these are probabilities, so they range from 0 to 1. They sum to 1, right? So if you fix the value of y and you sum over all x's, then those probabilities sum to 1. The probability that x lies between a and b, given some value of for y, well, you sum for all the x values that lie between a and b. You sum the conditional probability, keeping that y fixed at that value. Okay. Another example to illustrate our ideas. You roll 2 fair die. One die is red, the other one is blue. Let x be the result. Let y be the result of only the red die. What is the conditional PMF? Well, all right, let's do one value and then you can do the others as an exercise. The conditional PMF evaluated at x is equal to 3, given y is equal to 1, is a probability that you get a total 3. That's what x is. And the red die result, that's what y is 1. That's the probability that the blue die had to give you 2. You had a 1, the other one must have been a 2 to give you a total of 3. The probability of rolling a 2 is the same. Okay, so you use that kind of reasoning and you give a complete definition for the conditional PMF. Okay, Bayes theorem. Well, basically, the conditional PMF for x given y was the joint PMF evaluated at xy divided by the marginal evaluated at y. Now the joint PMF, if we want, it can be replaced by f sub xy. That's the probability that x equals x and y equals y. That's the same as the conditional probability that y is equal to y, given that x is equal to x, times the marginal for x, divided by f sub y. Okay, so this is Bayes' theorem, and in some cases, this conditional probability might be given or it might be easy to figure out, and this one might be harder, right? Y given x might be easier to find than x given y. Or it might already be given to you, and you might need to find out x given y. Okay, so this is a way of using y given x to figure out x given y. Okay. Similarly, f sub the conditional for y given x is equal to the conditional for x given y times the marginal for y divided by the marginal for x. Okay, so f sub xy, we want to find the marginal distribution for f sub xy given for x is equal to 3, given that y is equal to 1. Okay. So we find the marginal for 3, 1. Let's say it's 1, 6, 1 over 36. And the marginal for 1 is 1 out of 6. So we get 1, 6. Okay, in the special case, for statistically independent random variables, remember the conditional for x given y is the PMF for the joint PMF for xy divided by the marginal for y. But in the special case of independent random variables, the marginal here is the joint PMF is the product of the marginal PMFs. And then the marginals for y cancel, and you get left with f sub x of x. So the marginal for x given y, if x and y are statistically independent, is just it's the same as the PMF, the marginal PMF for x. Similarly, if x and y are independent, then the conditional for y given x is just the marginal for y. Okay. Law of total probability. You remember that if you have the joint PMF for x and y, and you sum out all the y's, then you are left with the marginal for x. Now, if you take the joint for x and y, and you use the product rule, then that's the same as the conditional for x given y times the marginal for y. Okay, so you can rewrite your f sub x of x. You can rewrite your marginal for x on the left-hand side. You can replace it by this on the right-hand side if you like. Remember that this appears, for example, in our Bayes rule, so you can replace the denominator in the Bayes rule by this if you like. Okay, similarly, the marginal for y is given by summing out all the x's, and you can replace the PMF, the joint PMF for x and y, with the marginal for y given x times the conditional for y given x times the marginal for x. Okay, so now, for example, if you wanted the marginal for 3, evaluated at 3, you would sum over y, the conditional for x fixed at 3, and y taking all allowed values, times the marginal for y. Okay, so you could have y is equal to 1, you could have y is equal to 2, you can't have y is equal to 3, right? Because x was the total of the row, right? So you get numbers bigger than 3 if y was 3 or the other numbers. So y can really only be 1 and 2. Okay, so you use this formula, allowing y to be 1 and y to be 2. And then, all right, so the probability that x is equal to 3, given that y is equal to 1, that's the probability of rolling a 2, is 1/6, times the probability of rolling a 1, which is 1/6, plus the margin and the probability that x is equal to 3, given that y is equal to 2, that's the probability that x is equal to 1. Right? That's the probability that the roll on the other die is a 1, that's 1/6, times the probability of rolling a 2, that's 1/6. So it's 1 over 36 plus 1 over 36 is 1 over 18. Okay, so that's how to get a few results for the marginal distribution, for the marginal PMF from the conditional or joint PMFs. Okay, now we have an idea of conditional expectation. So you can have the expectation of x, or you can have a conditional expectation. What's the expected value for x given that y is some fixed value? Okay, so the expectation of x given that y is some fixed value, well, if you just wanted the conditional for the expectation of x, you would sum over all x times the PMF for x. All right. If you wanted the conditional expectation for x given that y is equal to y, you would sum over all x times the conditional expectation, with y being fixed at that particular value. Okay, so for example, if you want the conditional expectation for y is equal to 1, right? That's a summation over all x, so let x equal I, so I goes from 1 to 12. I was the sum of, right, the sum, so one die has up to 6, one die gives you up to 6, so two die together, their sum gives you from, their sum gives you from 2 to 12. Okay, so I should go from 2 to 12. Well, okay, so just let it go from 1 to 12. So I conditional expectation x is equal to I with y being fixed at 1. Okay. Well, really you only, the sums, if y is equal to 1, then the sum can only go from I equals 2 to I is equal to 7. The sum can only go from I equals 2 to I equals 7. Take I, and then once y is fixed, then the roll on the other die is fixed, and that probability for whatever that is 1/2. So you get 27 over 6. Okay. To make sure you understand, you want to go through the examples carefully and make sure that you get the numbers that I did. Or I made a mistake. You want to correct my mistake. Okay. So that was the discussion of conditional PMFs for discrete random variables x and y that give you the probability that x gives a value, takes a certain value, given that y is taking some specific value.